Hey, so this series is going to be on Ahlfors complex analysis. The title of this work is in the description. But this is basically my notes, and I'm just going to kind of talk about make a series on this. So our journey basically begins with the complex algebra and geometry of complex numbers. So the title itself here just kind of signals the dual nature of our exploration. So we're first going to kind of establish fundamental rules of engagement. So just the algebra of complex numbers that govern these kind of, I guess, we're going to treat this as if we've never seen them before. So these are new mathematical objects. And then we're going to immediately translate these rules into a visual, kind of lucid framework. So the geometry, basically, or at least the algebra of the geometry. So this basic, or this inequality here, if you haven't seen it before, it's the triangle inequality, which basically states that the magnitude of the sum of A and B is less than or equal to the sum of their individual magnitudes. So this is not just a formula, but it's kind of a cornerstone for how we measure distance and understand relationships in this kind of new space, which is a foundational principle for everything that follows. So this still applies even in complex numbers. So excuse me. We're going to begin with a core definition. So a complex number, which we'll call Z, and Z from now on, is an entity that we've constructed from two real numbers, which we will call alpha and beta. It is written as Z equals alpha plus I beta. And so here, this I, we're going to define it as this revolutionary element. And it's a number that's defined as such that its square is -1. So this might seem kind of abstract, but it's no different than introducing a new type of, I guess, like asset to a portfolio or something. We're just kind of adding something in and just, seeing what happens. And this often happens in mathematics all the time. There's nothing wrong or irresponsible about this. We just throw it in there and let's see what happens. So the component then, alpha, is called the real part of Z, and beta is the imaginary part. So you can think of these as two distinct but related accounts, I guess, if I were to make these financial analogies. So for two complex numbers to be identical, for them to be identical to each other, they must be they're equal if and only if. So both their real and imaginary components must basically match perfectly. So there's no ambiguity between this. And the rules of their combination here are straightforward extensions of what we already know, which we mentioned in Shilov. But just for addition, we simply, combine the like terms, and the real parts sum together and the imaginary parts sum together, kept separate by their I little tag here that we tagged onto them. So, but over here. But multiplication here, sorry, I was looking at the wrong place. But multiplication here is a little bit more intricate. So when we multiply alpha plus I beta together by gamma plus I beta, I delta, for this new imaginary part, we have this rule, and it's not arbitrary. It's precisely kind of what's required for this new system to be consistent for the number I, to maintain this defining property here. And so this change here is just this one small change in the operation, right, from this definition that we've created, is responsible for basically this entire book. So that's basically it. So let's discuss this, right? So let's look at arithmetic operations. So division. So just as we can add and multiply, we can also divide, and this is kind of crucial. So for our system of complex numbers, to basically constitute a true number field, a self-contained and complete mathematical structure is the definition of a number field, right? Or a true field. For every non-zero element, they must have a multiplicative inverse. This must be true. So the question is, given two numbers, complex numbers, A and B, where B is not 0, of course, we can always find a unique quotient Z, or can we, I guess the question would be, can we find a unique quotient Z such that A equals B times Z? And by expressing A, B, and Z in terms of their real and imaginary parts, this single complex equation transforms into a linear of a system of two equations with real numbers. And so basically the determinant of the system is gamma squared plus delta squared. And so that's why it is, because it can't be equal to 0, or else it would be a degenerate matrix. We discussed that in Sheeloff. Yeah, while this proves existence, there's kind of a more direct computational method. So to find the quotient, we employ this technique of multiplying the numerator and denominator by what's called the complex conjugate of the denominator. Hence, the conjugate of gamma plus I delta is gamma minus I delta, and then this maneuver kind of is designed. It's convenient, and it makes the denominator a purely real number, which is very interesting quality of complex numbers. So basically gamma squared plus delta squared, thereby just simplifies the entire equation and expression into the final x plus iy form. And it's an elegant piece of, I guess, engineering to remove the imaginary part of the denominator to clarify the result. So let's just look at this kind of exercise just to see how this works. So we wanted to apply this division technique to a concrete example by finding the value of 5 divided by the quantity negative 3 minus 4i. And so, negative 3 plus 4i. And then, we identify the denominator's conjugate, which is negative 3 minus 4i. Then we multiply both the numerator and denominator by its conjugate. This is equal to multiplying it by 1 so that it doesn't change the value. And really think about this. I mean, this looks trivial, but I want you to think about this, what happens here, deeply. So the numerator becomes 5 times the quantity negative 3 minus 4i, right? And this simplifies to the square of its real part plus the square of its imaginary part. So negative 3 squared plus 4 squared, and this gives us negative 15 minus 20i in the numerator plus 9 plus 7 plus 16, and then which is 25 in the denominator. We then kind of separate the real and imaginary parts, yielding negative 15 over 25 for the real part and negative 20 over 25 for the imaginary part. Simplifying these fractions here gives us this final answer. So it's negative 3/5 minus I times 4/5. And so this is convertible to this via the conjugate of basically dividing rules. So just note this, that you can do this. It's not exactly trivial, but yeah, so now let's talk about square roots. So having established these 4 basic operations, we now ask a more advanced question, right? Can we take the roots of complex numbers? So specifically, can we find a complex number z equal to x plus y, whose square is another complex number, alpha plus I beta? So when we expand out the expression for z squared, we get this x squared minus y squared plus I times 2xy. Then equating this with alpha plus I beta gives us another system of 2 equations. This time it's nonlinear. So the first equates the real parts, x squared minus y squared equals alpha, and the second equates the imaginary parts, 2xy equals beta. So to solve this, we introduce a third equation derived from the magnitude. So the squared magnitude of z squared is x squared plus y squared all squared. So which must be equal to the squared magnitude of alpha plus I beta, which is alpha squared plus beta squared. And this gives kind of a clean expression for x squared plus y squared. And now with a system for x squared plus y squared and x squared minus y squared, we can solve for x squared and y squared individually. And these results are just simple expressions of involving alpha and the magnitude of the original number. So this crucial detail kind of remains, right? The signs of x and y are not independent. That's really important to see. So the condition, right, is 2xy equals beta. And this dictates that their product must have the same sign as beta. But the constraint ensures that for any non-zero complex number, there's exactly 2 square roots, which are the negatives of each other. So let's compute the square roots of I. Let's do that. What is the square root of I? I think that's an interesting thing to try to ask, and of course the solution's here. Here our target, right, alpha plus I beta, is 0 plus 1i. So alpha is 0 and beta is 1. We use the formulas we just derived. X squared is equal to 1/2 times the quantity 0 plus the square root of 0 squared plus 1 squared, which simplifies to 1/2. Y squared is 1/2 times the quantity, negative 0 plus the same square root, which is also 1/2. And this tells us that x and y must both be plus or minus 1 over the square root of 2. So now we apply the sign constraint. 2xy equals beta, and here beta is 1, a positive number. So this means that x and y must have the same sign. Therefore, our two solutions either both positive or negative, and the roots are 1 over root 2 plus I times 1 over root 2. And also we have negative 1 over root 2 minus I 1 over root 2. So these can be written more compactly as plus or minus the quantity 1 plus I all over the square root of 2. So we also want to basically just justify this. Why does the system work so well? So let's step back and look at the formal justification, right? The real numbers denoted by the symbol R, or math BBR, forms it for those of you who have LaTeX heads, but they form a complete ordered field. So, but you have to notice they're algebraically incomplete, right? So the simple equation x squared plus 1 equals 0 has no solution. So to remedy this, we construct a new field C that contains R. And the book's approach to Ahlfors' approach is to define complex numbers as an ordered pair of real numbers. It's like alpha and beta. And then it defines addition, multiplication rules for these pairs. But addition is straightforwardly component-wise. The multiplication rule then becomes alpha, comma beta, gamma, comma delta equals alpha gamma minus beta delta, and alpha delta plus beta gamma. This looks complicated, but I mean it's precisely the rule needed to ensure all the properties of the field hold. So within the system, then a real number alpha is represented by the pair alpha 0, and the imaginary unit I is defined as the pair 0, 1. So when you apply multiplication rule to I squared, or 0, 1 times 0, 1, you get negative 1, 0, which is our representation of the real number negative 1. So now we've really formally constructed what that our system is logically sound. So this is kind of a good achievement because it shows that the formal construction it really kind of also has some alternative constructions which are algebraically equivalent as well. And one is to view complex numbers as the set of polynomials with real coefficients. But with the rule x squared, or the rule that x squared can always be replaced by negative 1, basically. So another powerful representation is as a specific set of 2x2 matrices, which is, I think, really popular on YouTube right now. I've seen this everywhere, but I wanted to really rigorously get to here. So not just intuitively, but like as such. So matrix addition then and multiplication perfectly mirror the behavior of complex numbers. So this is basically a recurring theme in mathematics, right? A single abstract structure can have multiple equally valid concrete representations, each offering a different perspective. So, very interesting. This is the usefulness of complex numbers, and it all just had to do with basically just this introduction, just for the sake of introducing it. So let's now introduce a new concept. I can't remember what's next. I think is it conjugation? Yeah, conjugation. So we did talk about conjugates, right? And we're going to introduce kind of two fundamental operations. So the complex conjugate of the number is z equals alpha plus beta, and it's denoted by z bar. It's defined by alpha minus I beta. We've already kind of talked about this, but geometrically this is a reflection across the real axis. That's basically what it is, just reflecting it across the real axis. So a number is real if and only if it is equal to its own conjugate. So that's even another powerful way of thinking about it, right? So conjugation interacts predictably with arithmetic. So the conjugate of a sum is the sum of the conjugates, and this holds for products and quotients. So this property is incredibly useful and allows us to express the real and imaginary parts of z elegantly. And the real part is the sum, or half the sum, of z and z bar. So while the imaginary part is the difference between z and z bar divided by 2i, the second concept is the absolute value or modulus, written as the two vertical bars around z. So the modulus, and is written as it represents the number's magnitude. So it's the distance from the origin in the geometric picture. It's defined as basically the square root of alpha squared plus beta squared, and critically, the square of the modulus mod z squared is equal to z times z bar. And this link between magnitude and conjugation is central to many calculations. And I hope you guys really are enjoying kind of this meditation intensely on the idea of complex numbers, because really this is where the intuition for it comes. Like, I mean, we kind of do the math and we go through it, but I think really going through the rigor and kind of sitting through this is awesome. So thank you guys if you're here and you've made it all the way. So so this link between magnitude and conjugation, basically we have the modulus, right? It works well with multiplication and division. The modulus of a product is the product of the moduli. And finally, this basic slide, or this final part of the slide, describes parallelogram identity, which is a geometric law. So, geometric law relating the sums and differences of two complex numbers to their magnitudes. This comes from a direct consequence of these definitions up here. So let's work through this exercise, and we're going to find a fascinating identity that is key to understanding certain transformations in the complex plane, particularly those that preserve the unit circle. So we're asked to prove that the modulus of the fraction a minus b over 1 minus b bar a, or b bar b, a bar b, is exactly 1. And provided that either the modulus of a is 1 or the modulus of b is 1. So it doesn't matter which one. But we are also asked about any necessary exceptions. The most direct line of attack to this is to show that the square of the modulus is 1, which is the same as showing that the squared modulus of the numerator equals the squared modulus of the denominator. And we would use the fundamental property that the squared modulus of any complex number z is z times z bar. So this allows us then to expand both sides of the desired equality into expressions involving a and b, their conjugates. So let's execute this proof. We expand the squared modulus of the numerator, a minus b, which gives mod a squared minus 2 times the real part of b bar plus mod b squared. We do the same for the denominator, 1 minus a bar b, which expands to 1 minus 2 times the real part of a b bar plus mod a squared times mod b squared. And then hence from our original fraction, we have a modulus of 1, and these expressions must be equal to each other. So the 2 times the real part of a b bar is a common term to both, and it cancels out. So then we are left with the condition that basically mod a squared plus mod b squared must be equal to 1 plus mod a squared times mod b squared. And rearranging this equation, moving all terms on one side, allows us to factor into the product of 2 terms. So mod a squared minus 1 times 1 plus 1 minus mod b squared. For this product to be 0, at least one of the terms must be 0. And so this means either mod a squared equals 1 or mod b squared equals 1, which is precisely the condition we were given. So now for the exception. Division by 0 is undefined. So the denominator, right? 1 minus a bar b is 0 if a bar b equals 1. So if we assume both a and b have a modulus of 1, then a bar is simply 1 over a. And in this case, the denominator is 0 if b over a equals 1. So this means that a must equal b. Therefore, the identity actually holds under the given conditions, with a single exception, that if both a and b lie on the unit circle, they cannot be the same point. That's the way to interpret this. I would think about that a little bit. But really, it seems like a really basic proof, but you get some interesting ideas or interesting consequences from this. So, inequalities. So these are the languages of estimation and control. So for any complex number z, okay, its real and imaginary parts in magnitude are less than or equal to the modulus of z. This is geometrically obvious, as the length of a right triangle leg can't exceed the length of its hypotenuse. So the most important inequality of all complex analysis, and pretty much probably in any mathematical discipline, it's the most abused inequality ever, is the triangle inequality, or Cauchy-Schwarz, which is a generalized version of that. But the modulus of a plus b is less than or equal to the modulus of a plus the modulus of b, of course. So this proof is kind of revealing, right? It starts by squaring the left side, a mod b plus b squared, and then expanding using the conjugate. And the expansion involves the term 2 times the real part of a b bar. And since the real part of any number is less than or equal to the modulus, we can replace this term with 2 times the modulus of b bar, which is 2 mod a mod b. So this turns the expression into the perfect square of mod a plus mod b. Then taking the square root gives the result. And the inequality, so this is a little bit different because of the I, but or the properties of the modulus, but the equality holds only when a b bar is non-negative and it's a real number, which means that a and b have the same direction in the complex plane. So this concept then will generalize to any number of terms. And the direct consequence is the reverse triangle inequality, which provides the lower bound for the modulus of a difference. So the magnitude of mod a minus mod b is less than or equal to the modulus of a minus b. So this tells you that the difference in the length of 2 sides of a triangle cannot be greater than the length of the third side. And so then we can generalize to Cauchy-Schwarz. I kind of anticipated that on accident. But this is the cornerstone of linear algebra and probability theory and other fields. But basically linear algebra and probability theory, or measure theory, I guess. And here, it appears in its complex form. So we can establish this powerful relationship between 2 complex vectors. No, sorry, 2 complex numbers. Sorry. Let's say a set of a sub I and a set of b sub I And this states that the squared modulus of the sum of products a sub I times b sub I is less than or equal to the product of two sums, the sum of mod a sub I squared, and the sum of the mod b sub I squared. You can kind of think about this all together, right? Think about the a's and b's as vectors. So I accidentally said vector, right? But that's kind of how I was thinking about it, because this inequality relates their inner product to their individual lengths. So the proof outlined here is actually profoundly insightful. It generates a new quantity, the sum of the squared moduli of a sub I minus lambda b sub I, where lambda is an arbitrary complex number. And so since this is the sum of non-negative real numbers, it itself must be non-negative. Then we expand the expression to get the quadratic and lambda. And the core insight from this is just to choose a value of lambda that minimizes the expression. And the optimal choice, akin to finding the best hedge to a minimum variance in a portfolio or something. Maybe not exactly, but well, I mean, it's very similar. Basically, lambda equals the sum of a sub I b sub I bar over the sum of mod b sub I squared. And then when we substitute this value back into the inequality, it simplifies and reveals the Cauchy-Schwarz inequality itself. And this inequality holds if and only if one vector is a scalar multiple of the other. What does that mean? That means it's linearly independent. So, yes. Let's shift our focus to geometry. So we have algebra. We have, imaginary numbers and all this stuff. Let's go to geometric, or the geometry of it. I'm not going to actually visualize this, but I want you to think about this. Let's think about it with our brains, because we're going to have to get used to this for really higher dimensional spaces, even though the complex plane is only two-dimensional. But that's besides the point. I'm trying to get better at this myself. So let's visualize a complex number, right? Imagine it as z equals x plus I as its point xy. So in a two-dimensional Cartesian plane, we're going to call it the complex plane from now on. So the horizontal axis is the real axis, and the vertical axis is the imaginary axis, and the number z can be seen as a vector, or some arrow pointing from the origin to the point xy. And the length of this vector is precisely the modulus of z. So this modulus is really specific to complex numbers. Remember, it was z times z bar. So the distance between those two complex numbers, a and b, is simply the modulus of their difference, x minus b. I want you to close your eyes and imagine that, right? So I'm going to narrate. Close your eyes. I'm going to narrate you through this. This is not weird, I promise. So the length of this vector, right, that's z, right? This is being seen as a vector. It's pointing from the origin to the point xy. And the distance between two complex numbers, a and b, is simply the modulus of their difference, a minus b. So this geometric viewpoint here makes the arithmetic intuitive. You can open your eyes now, by the way. Sorry that was cringe and you clicked off. Too bad. But thanks for saying if you're bearing with me. But the addition basically of two complex numbers a and b follows the parallelogram law of vector addition. So the conjugation, taking z to z bar, is a reflection across the real axis, and by taking z to negative z, it's a rotation by 180 degrees around the origin. So this one-to-one correspondence between complex algebra and planar geometry is the source of immense power and insight. So while vector addition is a good geometric model for complex addition, multiplication requires a new perspective. So for this, we introduce polar coordinates. Any non-zero number, z, can be uniquely described by its distance from the origin, its modulus r, and the angle its vector makes with the positive real axis, its argument phi. And the number then can be written as z equals r times a quantity cosine phi plus I sine phi in its polar form. So when we multiply two complex numbers, z1 and z2 in their polar forms, remarkably simplification occurs very naturally. So by using trigonometric sum identities, we find that the product R1 times R2 multiplied by cosine of phi1 plus phi2 plus I sine of phi1 plus phi2. This rule kind of is stunningly simple to multiply two complex numbers. We then multiply the moduli of their arguments. So algebraically complex, the operation becomes geometrically trivial. So it's basically a combined scaling and rotation. So this is a surprising property of complex numbers that the mathematicians first working within the rules of this space and applying the field axioms kind of we're finding some weird coincidences. So this multiplicative rule leads directly to one of the most famous formulas in complex numbers, De Moivre's formula. I don't know how to say it. Oh, sorry. But by applying the rule repeatedly, we can see that raising a complex number z to an integer power n results in r to the n times the cosine of n phi plus I sine of n phi. We raise the modulus to the nth power and multiply by the argument n, and this is a very powerful computational tool. It allows us basically to solve the binomial equation. So z to the n equals a for any non-zero complex number a. We're essentially looking for the nth roots of a. And by expressing both z and a in polar form, we can equate their moduli and arguments. And so often this is shown, this De Moivre's formula is shown in or at least I saw this in high school, like around, my sophomore or junior year, I can't remember. But it showed up and we were like, oh, okay, you can just use it. And it always fascinated me how it works all the time. But, this is basically from a rigorous standpoint, how it kind of emerges. So basically, by equating their moduli and arguments, the modulus of z is the nth root of the modulus of a. And then the argument of z, when multiplied by n, must equal the argument of a. So their angles, though, must be periodic. So we must account for all possible full circle rotations. So n times theta equals phi plus 2k pi, where k is any integer, and then this will yield n distinct solutions for theta corresponding to k from 0 to n minus 1. And these n roots are all located on a circle where the vertices are a regular n-sided polygon. So there's a lot of geometry that's emergent from this idea. And by the way, the fundamental theorem of algebra here is at play here, which would generate n roots for an nth degree polynomial or nth degree equation. So let's use this machinery, right, to find the four fourth roots of -1. So we first write -1 in polar form. Its modulus 1 is its argument is pi radians, or 180 degrees. And we're looking for z such that z to the fourth equals 1 times cosine of phi plus I sine of phi. And using our formula, the modulus of each root will then be the fourth root of 1, which is 1. The arguments then will be pi plus 2k pi, all divided by 4. And then taking k values to 0, 1, 2, and 3, this gives us 4 distinct angles: pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So let's do that. When we do that, we calculate the roots explicitly. For k equals 0, we have cosine of pi over 4 plus I sine pi over 4, which is 1 over root 2 plus I times 1 over root 2. And then for k equals 1, we can do the same for k equals 2, for k equals 3, and the final root. Basically, as predicted by the theory, right? As we predicted by the theory, these 4 points form the vertices of a square inscribed square in the unit circle in the complex plane, which is perfectly symmetric around the origin. So as you can probably anticipate, there's a lot of weird geometric things or coincidences that are happening with the language of complex numbers. So it basically provides an exceptionally compact way to describe geometric figures. So a circle with center A and radius R is the set of all points Z, such as the modulus of Z minus A equals R. And by squaring this and using the conjugate property, we can write this as an algebraic expression or equation involving z and z bar. So a straight line can be thought of as a circle with an infinite radius. That's a different way to think of a straight line, right? So it's equation, and if you ever seen like a polar form for a straight line, isn't like secant, or I can't remember, like secant or cosecant or something. But basically, it takes this is how we do it. So the book, right, that Ahlfors shows, he kind of shows that the both the figures, circles and lines, can be described by a single equation in general form. So for both circles and lines, we have that a times z bar plus bz plus b bar z bar plus d equals 0, where a and d are real. So if a is 0, the equation describes a line. If a is not 0, it describes a circle. And by completing the square, completing the square, one can easily extract the circle's center from the radius, and the radius from the coefficients a, b, and d. So this unification here is just not some notational convenience. It basically hints at this deeper geometric connection between lines and circles, which is profound. So this exercise here will show this beautiful geometric property that's related to inversion. So a fundamental transformation in complex geometry. We're going to be asked to show that any circle passing through a point A and another point over A bar will intersect the unit circle at a right angle or orthogonally. And the point 1 over A bar is the inversive image of A with respect to the unit circle. So it's like inverse image, basically. It's like inside. And the problem requires us to connect the algebraic condition of the circle passing through these specific points with the geometric condition of orthogonality. So we're also getting some more things out of this. We will use the general equation of a circle and an algebraic condition for when two such circles intersect at right angles, essentially. So this condition B1, B2 bar plus B1 bar B2 equals A1D 2 plus A2 D1. And this is a compact way of just basically checking for orthogonality without calculating angles directly. So let's just lay out the proof now. We take this general equation for our circle C, and for simplicity we set its leading coefficient a to 1, the unit circle C is 0, has the equation z bar minus 1 equals 0. And then plugging in the coefficients for C and C0 into the orthogonality condition, we find that it simplifies the requirement that the constant term d in our circle equation must be equal to 1. Our task now is just to prove that the circle passes through A and 1 over A bar, then d must indeed be 1. And then we write down the two equations that result from substituting these 2 points into the circle's equation. And the second equation involving 1 over A bar can be multiplied through by A bar to clear the fractions. And then this will then give us 2 algebraic constraints. So by, I guess to put it clearly, right, we cleverly kind of combine these 2 constraints, specifically by substituting the expression for BA bar, A plus B bar A bar into this from the first into the second. Then we arrived at the factored equation. So 1 minus d plus 1 minus mod A squared equals 0. Assuming A is not on the unit circle itself, so mod A is not 1, and the second factor is non-zero. So then therefore we can conclude that the first factor, 1 minus d, must be 0, which means d equals 1. This is precisely the condition for orthogonality. We have shown then that algebraic constraint forces it forces the geometric property. So let's look at spherical representations. Why not, right? So to complete our geometric picture, we need a way to handle infinity. So what we're going to do is extend the complex plane by adding a single unique point at infinity. So this space here is the extended complex plane. This is a newer space that we're just going to kind of define, and we're going to define the rules for arithmetic operations involving infinity, such as a plus infinity is infinity, or a divided by 0 is infinity. So while this is algebraically kind of convenient, it begs for some kind of geometrical model, right? And what we are defining here is called the Riemann sphere. So we want to imagine, close your eyes again, we imagine a unisphere sitting in the complex plane, touching the origin. And then, at every point on the plane, it'll correspond to a unique point on the sphere, and vice versa. So this is a mapping of which we call stereographic projection. You can open your eyes now. Stereographic projection provides the explicit link between the plane and the sphere. So to map a point P on the sphere to a point Z on the plane, we draw a straight line from the north pole of the sphere through P until it intersects the plane. So the point of its intersection is Z, and this maps to the entire sphere of the entire plane, with one exception. So the north pole itself, right? Where does it go? As our point P gets closer and closer and closer to the North Pole, its corresponding point Z on the plane shoots further and further away in all directions. So the North Pole, therefore, corresponds to our single point at infinity that we created here. This creates a perfect one-to-one correspondence between the entire Riemann sphere and the extended complex plane. So, this slide really just shows the explicit formulas to convert between the sphere's coordinates and the plane's complex coordinate Z. You can find these in the book. But this projection has a remarkable property. It is what we call conformal. So that means that it preserves angles. And even more beautifully, it maps any circle drawn on the sphere to either a circle or a straight line in the plane. I want you to think about that. So a circle on the Riemann sphere becomes a line if and only if it passes through the North Pole. Think about that one more time. The circle on the sphere of the Riemann sphere becomes a line if and only if it passes through the North Pole. So this is a deep geometric reason why lines are unified in the complex plane. They are both just shadows of circles on the sphere. The I can't remember the next part. Oh, the chordal distance. So this one I kind of struggled with a little bit, but on the infinite plane, right? The infinite complex plane, the standard distance measure becomes problematic when we deal with the point at infinity. Because we just kind of said, yeah, just let there just be a point, right? That's just infinity. So we could have those properties, right? It works out algebraically, but the Riemann sphere, the idea of this offers a solution for this. So the chordal distance between 2 points in the plane is defined as the actual three-dimensional Euclidean distance between their corresponding points in the sphere. And so we're going to call this new distance metric d of z and z prime. It has the desirable property of actually being bounded. So the formula given here, and it relates to the chordal distance of the standard complex modulus. So at one point, say z prime, as it goes to infinity, its spherical image approaches the North Pole. So the formula for chordal distance to infinity, d of z infinity, shows that this distance is actually well defined and finite for any point z. This completes the geometric structure, giving us a space where infinity is a point, just like any other, where distance is always finite. So, looking at this exercise, it's asking us to prove a geometric relationship on the Riemann sphere using the algebraic language of the complex plane. So we need to show here that 2 points z and z prime correspond diametrically. These correspond diametrically to opposite points on the sphere if and only if their product z times z bar, or z prime bar, equals -1. This creates a direct link between an algebraic condition and a purely geometric one. So these are called antipodal points. our strategy will be to use the sterographic projection formulas to translate that we have here, to translate the geometric condition of p prime equals negative p onto an algebraic statement about z and z prime. So try to see if you can attempt this one by yourself. With this, you can pause. So the solution would be, let the spherical images of z and z prime be p and p prime, with the coordinates x1, x2, x3, and x prime 1, x prime 2, x prime 3, respectively. And so basically, if they're diametrically opposite, then the coordinates p prime are the negatives of the coordinates p. So then we use the projection formula to write z prime in terms of the coordinates of p prime. Then substituting the negative coordinates of p, we get the expression for z prime in terms of x1, x2, and x3. Then we compute the product z times z prime bar, and we substitute the projection formulas for z and z prime bar in terms of the spherical coordinates. Then after some algebraic simplification, the numerator becomes negative, so x1 squared plus x2 squared, and then the denominator becomes 1 minus x3 squared. Then since the point P is on the unit sphere, we know that x1 squared plus x2 squared plus x3 squared equals 1. So this implies then that the denominator 1 minus x3 squared is exactly equal to the numerator's x1 squared plus x2 squared, where the fraction simplifies to negative 1, and the reverse direction of the proof follows by working backwards from the algebraic condition to the geometric one that we derived. So let's kind of synthesize everything that we've discussed in chapter 1. So the first chapter has laid the essential groundwork. So we established that the complex numbers as a complete, algebraically closed field. We have seen that their algebraic rules have a direct intuitive geometric interpretation. This transforms multiplication into rotation and scaling. So de Moivre's formula gives us a bridge between exponentiation and trigonometry, while the Riemann sphere provided a geometric model that elegantly incorporates the point at infinity, which we just kind of shoved in there, right? From our need for a point at infinity. We then unify the geometry of lines and circles, and this foundation is not just an academic kind of exercise, but we're moving forward. The concepts of modulus, conjugation, and the geometry of the plane will be indispensable for defining core ideas of complex calculus. So, as you can imagine, there are rules in calculus that emerge from our idea of just introducing I squared equals negative 1. So, limits, continuity, most importantly, right, differentiability. That's one thing that we want to understand. Like, what is continuity in the complex plane, right? So the structures we've built right here are upon the bedrock of which the entire edifice of complex analysis rests. And this was all just a consequence of just saying this guy here. So I hope you guys enjoyed this introductory part of the chapter. I'm going to be going through this entire book with every single other series on my channel. And, just got to find time to record everything. But, yeah, I put a lot of hard work into this and worked through some of the problems and derived some interpretations and explanation to make this intuitive. But, yeah, the whole idea is just to show that there's an algebraic and geometric perspective of complex numbers, and they're kind of unified in their interpretations. And this is gonna be a continuous theme throughout the entirety of the of this series. So thank you guys so much for watching, and stay tuned for next time. And go ahead and check out my other videos too on physics and other mathematical things. Like I'm starting a differential geometry one too. So thank you. Bye bye.